Hello, today we're continuing in our A-level physics revision series looking at the subject of special relativity. You can find more advanced videos on this subject in my playlist on special and general relativity. Special relativity applies to inertial reference frames, which essentially means non-accelerating frames. That is to say that in special relativity people are either stationary or they're moving at constant velocity. And relativity means that you and I have different relative perspectives on the same event. Let's suppose that you and I are in boxes. Here am I, this is me, and this is you. And all we can do is to see each other through a little peephole. We have no means of seeing anything else that might serve as a reference point. What we can see is that we're travelling away from each other. So this distance is getting larger. I might think that I am stationary and you are moving away with a certain velocity v to the right. You might think that you are stationary and I am moving away with a certain velocity to the left. Or it could be that we are both moving away from one another with a combined relative velocity of v. But here's the thing, there is nothing you can do, no experiment that you can perform that can establish whether one of us is stationary and the other is moving away, or maybe that both of us are moving away. All the laws of physics will behave in exactly the same way if we are stationary or if we are moving at constant speed. If you are juggling, if you are playing snooker, all of those things will work just as well in a moving frame at constant velocity as they do in a stationary frame. That is not true in an accelerating frame. If one of these is accelerating and you try to juggle, the balls will fall because they won't land in your hand as you expect them to do so. Now, the special relativity as we understand it today all derives from an experiment performed by two people called Michelson and Morley. And they were trying to find the speed of Earth through space. They called it the ether, the speed of Earth through the ether. They knew that the Earth went round the Sun. They knew that the Sun went round the galaxy. But the real question was, how did Earth move relative to space itself? And they based their experiment on this principle. If you take a river that is flowing at, let's say, 3 miles an hour, and you have a rower who can row in ordinary still water at, let's say, 5 miles an hour, and you say to that rower, I want you to row across the river and then come back again, and we will time you, then the rower, of course, will not row across, because if he does, the river will carry him downstream. So the rower has to row in that direction at 5 miles an hour, and the river will push him so that, in fact, his actual transit across the river is in that direction. The river is flowing at 3 miles an hour. He's flowing in this direction. He's travelling at 5 miles an hour in that direction. We all know that the 3, 4, 5 triangle, or you can use Pythagoras to show that the actual speed across the river will be 4 miles an hour. And that will be true when he comes back as well. So if the river is 1 mile wide, then the rower will have to row across and back, that's a total of 2 miles, at 4 miles an hour. The total time to cross and come back will be half an hour. Now let's say the rower, we want you to row 1 mile, that is the same as the width of the river, 1 mile downstream, and then we want you to row back again. Well, when the rower is rowing downstream at 5 miles an hour, the river will also carry him at a further 3 miles an hour because the river is flowing. So he'll go downstream at 8 miles an hour. And that mile will take him 1/8 of an hour. But when he rows back at 5 miles an hour, he's rowing against a river which is flowing at 3 miles an hour. So his net progress will be only 2 miles an hour. And therefore the mile that he has to travel to get back will take him half an hour. And that means that the total time to travel there and back will be 5/8 of an hour. And the critical thing is that that is different from the half an hour it took to row across the river and back. So in other words, even though in still water the rower travels at 5 miles an hour, when he's going across the river and back it takes half an hour, but when he goes the same distance downstream and back it takes 5/8 of an hour. Now, if I hadn't told you that the river was travelling at 3 miles an hour, but I had given you all the rest of this information, you could have calculated that the river was flowing at 3 miles an hour. And Michelson and Morley took that self-same principle, and what they said was, if we can do a same kind of idea of getting something to travel across and back and down and back, and measure the difference in the time it takes, then essentially we can measure the flow of the Earth through space, because that's essentially the equivalent of the river. Instead of using a rower, Michelson and Morley used light. What they did is they took one light beam and they took it to a mirror that was a beam splitter essentially. It's half silvered and half allows light through. So some of the light was reflected up to a mirror up here, and some of the light went through the mirror and to a mirror here. And these distances are about the same. You can't make them exactly the same, but about the same. And then of course the light would be reflected from the mirror and come back again, where it would hit this half silvered mirror, and some of it would go straight through. This beam would be reflected and that would come down to an eyepiece. So you've got light that is reflected that way or goes through the mirror that way, and when the light beams come back they recombine at this mirror and come down to an eyepiece. Now because you've got a single beam of light that's been split and then rejoins, you're going to have an interference pattern, which basically means you're going to see a series of fringes. And those fringes will be light, dark, caused by interference. It's the same principle as ripples on a pool interfering with another set of ripples. You can see this in my video on waves. But here's the important thing. If you now move or rotate this whole experiment, take the whole thing and rotate it, then it's a bit like the rower, instead of rowing 1 mile in that direction, rowing 1 mile in that direction, or 1 mile in that direction, or 1 mile in that direction, or 1 mile in that direction. And as we've seen, the time taken for each of those would be a little bit different because of the effect of the river. So the idea is that if the Earth is travelling through space at a certain speed, then if you rotate this experiment, then the time taken for the light to travel to the mirror and back will be slightly different. And consequently, the interference pattern will be different. So as you rotate the experiment, these fringes will move. And measuring the extent of the movement of the fringes will enable you to calculate what the speed of the Earth is through the ether. So Michelson and Morley did this experiment. But the trouble was, every time they moved the equipment, the fringes didn't change. And that suggested that the amount of time it was taking for the light to travel there and back, didn't vary according to the rotation of the equipment. That's rather like saying that the time it takes for the rower to go up and down or side to side is exactly the same. But we showed that it wasn't and couldn't be if the river is travelling at 3 miles an hour. Of course, it would be the same if the river wasn't flowing at all. If this was just still water, then of course the rower's time going a mile across the river and a mile downriver would be exactly the same. So that's one possible conclusion of the Michelson and Morley experiment, that the Earth isn't travelling through space at all, it is stationary. But that's not a very likely outcome, since the Earth we know goes around the Sun, we know the Sun goes around the galaxy, so it's impossible for the Earth to be stationary in space. The other conclusion that you'd have to come to, therefore, is that the time it takes for the light to travel this distance is irrespective of any movement by the Earth through the ether. That is to say that the speed of light, c, is constant, independent of the speed of the observer or the speed of the source. And that turns out to be a critical point when it comes to special relativity. Why is that? Well, let's consider you on a train. There you are. And the train is travelling at this direction at 30 miles an hour. And you have a small ball which you roll along the corridor of the train in the direction that the train is moving at 10 miles an hour. What does an observer, that's me, standing on the platform, observe as the train goes by? I see a ball on the train travelling at 10 miles an hour, but the train itself is travelling at 30 miles an hour. So I will observe that the speed of the ball is 10 plus 30 equals 40 miles an hour relative to me. It travels at 10 miles an hour relative to you, but because the train itself is travelling at 30 miles an hour, I say that the ball's total speed is 40 miles an hour relative to me. Now let's do exactly the self-same experiment. Here are you on the train, which is travelling at 30 miles an hour. And instead of having a ball, you shine a torch. And the speed of the light that comes out of that torch will be c. I am standing on the platform and I measure the speed of that light. Now you would think that the light should be c, the speed on the train, plus 30, the speed of the train, in exactly the same way as we had up here. But that would be wrong, because according to Michelson and Morley, what I will measure is that the speed of the light is c, the same speed that you measure, irrespective of the speed of the train. And as we shall see, that has some rather intriguing consequences. So let's see why. Let's imagine that I am once again the observer, this is me, and I have marked out my frame of reference. That is to say, I've effectively put meter sticks along the ground and I've marked off every meter right the way along the ground, and that's my measuring scale. You are travelling, if you like, on a train. Here are you, and you've got your own measuring system on your train. Along the corridor of the train you've marked off meter elements. And the train is travelling at a speed v. This is you, this is me. And just to distinguish any measurements we may make, I'm going to say that all the measurements in your time frame, measurements of distance will be x prime and measurements of time will be t prime, whereas in my frame, measurements of distance will just be x and measurements of time will be t. So wherever we put a prime, that's what you measure. Wherever we don't put a prime, that's what I measure. And I can draw a space-time diagram. That is simply time here, space here. I'm using x and t because those are my measurements. And I can plot your velocity. That will be a straight line because you're going at constant velocity. Special relativity requires that. You're going at constant velocity, and I can measure that velocity. It's simply the distance you travel, x, divided by the time you take to do it, t. And that is the line of your velocity. I could incidentally also measure the speed of light. That will be c. By convention, we tend to draw the speed of light at an angle of 45 degrees. But the point about this is that the scale has to be such that this is the speed of light. So, for example, if this is 1 second, then this has to be 3 times 10 to the 8th meters because light travels at 3 times 10 to the 8th meters per second. Now, how do I calculate how far you have travelled? Well, here we are. This is me on my graduated scale. And here is you travelling at speed v in this direction. And I will say that you have travelled this distance, which is x, measured on my scale, in time t. And that means that your velocity is simply the distance you've travelled divided by the time. V is x over t, or if you like, x equals vt. By contrast, you are standing on your scale, and you are saying, compared to my scale, compared to the scale that's on your train, you're not moving at all. Because you and the scale are both moving at v. So compared to the scale, you are not moving. So you say that in your frame of reference, x prime, which is the measure in your frame of reference, is 0. That is to say, you are not moving with respect to your frame of reference, because both you and the frame of reference are on the train. So the frame of reference and you remain in the same place relatively. So you say, you're not moving. I say, you are. Now then, if x equals vt, then x minus vt equals 0. But x prime equals 0. And so we get that x prime is equal to x minus vt. All we're doing there is comparing your assessment according to your scale with my assessment according to my scale. And of course, for the moment, we are going to assume that when we each measure time, we measure the same time. So the assumption that we're going to make is that the time that I measure, t, will be the same time that you measure, which is t prime. That we are going to discover is actually not correct. But it's an obvious thing, so we'll assume it for the time being. And how can we make that happen? Well, what we can do is we can have a situation whereby as you, this is you, and this is me, as you pass me, travelling at v, we can have an arrangement whereby there can be a very short contact between our two boxes, which synchronises the watches or the clocks on both of our relative locations. And that means that at some time in the future, when you have reached here, I'm still here, you've reached here, we would say that if 5 seconds has passed on my watch, 5 seconds will also have passed on your watch. We can each, of course, also measure the speed of light in our respective frames. And I will say that the speed of light is the distance travelled divided by t, and you will say that the speed of light is x prime divided by t prime, because we are each measuring in our own frame of reference. But Michelson-Morley says that we will both get the same result. So now let's just take the formulae that we've just derived and see what comes from them. Firstly, we established that x prime equals x minus vt. That was simply to compare you saying that you don't move in your frame of reference, and I say, but you do move in my frame of reference. We also established that c is x over t, which means that x equals ct, and we established that c is x prime over t prime, which means that x prime is ct prime. So let's feed these into this formula here. X prime is ct prime, so up here, x prime is ct prime equals x, well that's ct, minus vt, which means that ct prime is equal to t into c minus v. Now, if t prime equals t, which is what we think is the case, the clocks remain synchronised, then we have that c is equal to c minus v. And that obviously cannot be true unless v is 0. But v is not 0 because you are moving relative to me. So we've arrived at a nonsense. Something has gone wrong somewhere. What has gone wrong? Well, let's go back to our starting position again, which is that x prime is equal to x minus vt. And if that's the case, I can simply reorganize that to say that x equals x prime plus vt. And since we're assuming that t prime equals t, I can put a prime on that so that both of these terms are measurements that you will make. So this is what measurement you make compared to the measurements I make. This is the measurement I make compared to the measurements you make. But something's gone wrong. So we are going to take these two terms and we're going to put an error term in them. Essentially, we're going to multiply both by an error term called gamma. We're going to say somewhere we've made a mistake. So let's make that mistake equal to gamma and see if we can find out what gamma is. To work out what gamma is, what we're going to do is we're going to multiply both sides of these equations together. So we're going to have x prime times x is equal to this term times this term, which is x minus vt times gamma times x prime plus vt prime times gamma. And that's going to come out as x prime x equals, well, let's first take the two gammas. That's going to give you gamma squared into, now we've got to multiply these two terms in brackets. So x times x prime is x prime plus x vt prime minus vt x prime minus v squared t prime. All I've done is to multiply that bracketed term by that bracketed term. Now, it's all beginning to look a bit horrendous, but we remember that we determined that the speed of light was x over t, and the speed of light is x prime over t prime. It's constant, whoever's measuring it. And that means we can say that t is equal to x over c, and t prime is equal to x prime over c. Substitute these values for t and t prime into this formula here. What do we get? We get that x prime x is equal to gamma squared from here into x prime, well that's that, plus xv. Now instead of t prime I'm going to put x prime over c, minus v, and instead of t I'm going to put x over c times x prime, minus v squared, and instead of t prime I'm going to put x over c, x prime over c. So I've simply, in this formula, replaced all the t's and t primes by x over c or x prime over c respectively. Now again, that still looks awful, but you'll notice that x prime exists in every term. So I can divide throughout by x prime. If I divide this by x prime, I get 1 equals gamma squared, because that remains the same, into. This becomes 1 plus, if you divide that term by x prime, you get v over c. If you divide that term by x prime, you get minus v over c. And if you divide this term by x prime, you get minus v squared over c squared. And now you'll see that these two terms cancel. And so we've now got that 1 is gamma squared into 1 minus v squared over c squared. Or, if you prefer, gamma squared is equal to 1 divided by 1 minus v squared over c squared. Or gamma is equal to the 1 over the square root of 1 minus v squared over c squared. And that gamma is called the Lorentz transform. So what we're saying is that whereas we originally wrote that x prime equals x minus vt, which was simply comparing what you think in your frame of reference to what I think in my frame of reference, what we should have done is to multiply this term by gamma, which is the error term, and gamma is 1 over the square root of 1 minus v squared over c squared. So actually, that is what we should have had, and that's the relativistic correction. Now you'll notice something. that if the velocity is very, very, very much less than c, the speed of light, that v squared over c squared becomes effectively 0. And therefore you're just left with the square root of 1, which is 1, and that means that x prime equals x minus vt, which is what we thought was the case all along. It's only when v approaches or gets close to the value of the speed of light that this relativistic term comes into effect. So what we've shown is that special relativity, or the Lorentz transform term, has an effect as v gets very large. For ordinary speeds that we are used to, for example the train, it has no effect. That's why the ball rolling on the train, all you had to do was to add the speed of the ball to the speed of the train. But when you get to something travelling at or near the speed of light, this term becomes the square root of 1 minus v squared over c squared becomes very important. Let's each measure a rod in your world. So here you are on your world travelling at speed v, and you have a rod. This is you. This is me. In my world, you have a measuring scale, I have a measuring scale. Your measuring scale is x prime and t prime, my measuring scale is x and t. Now, the first thing we have to understand is that when I measure the length of the rod in your frame, I will have to measure both ends simultaneously in order to get the reading on my scale. If I measure this end first and then go away and have a cup of tea and come back and measure this end, you will be here, and I will measure that the length of the rod is some absurd distance because I allowed time to elapse between measuring each end. So I've got to measure both ends simultaneously, otherwise you'll move and I'll get the wrong reading. So for me, t must equal 0 because I've got to measure both ends at once. So if we take this formula here and make t equal to 0, then I get that x prime is equal to x divided by the square root of 1 minus v squared over c squared, because t in this formula is 0. And so it just reduces to this formula here. Now remember, x prime is the local. That's what you are measuring in your world. X is remote. That is to say, I am measuring the distance remotely. So always remember, x prime is the local measure, x is the remote measure. So we can rearrange this formula here to say that x is equal to x prime into the square root of 1 minus v squared over c squared. And you'll notice that the square root of 1 minus v squared over c squared will always be between 0 and 1. If v is very small, then the v squared over c squared term becomes vanishingly small, almost 0, and this term becomes 1. If v is the same as the speed of light, then v squared over c squared is 1, 1 minus 0 is 0, and so this term becomes effectively 0. And so the transform term is going to be between 0 and 1. And that means that x is always going to be less than x prime. X prime is what's measured by you locally with your rod. X is the distance I measure your rod to be remotely. And that means that I will say that the length of your rod is shorter than you say it is. And that is called length contraction. A moving rod looks shorter. Now once again, you have to realise that if you're moving at 30 miles an hour, this term is going to be negligible. It's going to be 1. Or rather, this term, v squared over c squared, is 0. Therefore this term is going to be 1. So you won't notice any change. But if you were on a train moving at near to the speed of light and you measure the length of your rod to be 1 metre, I will measure it to be very much less than 1 metre, as we shall see in a moment. Now, what about time? Because we've always assumed up to this point that time is the same, that t equals t prime. Now, is that right? Well, I can tell you it isn't, but let's see why. Let's go back to our famous formula that x prime is equal to x minus vt multiplied by the Lorentz transformation, which I shall say is gamma. Remember that gamma is equal to 1 over the square root of 1 minus v squared over c squared. And we'll also remember from the speed of light that light is equal to x over t, and it's also equal to x prime over t prime, which means that we can take, let's just do it, x is equal to ct and x prime is equal to ct prime. So let's substitute these values into this formula. So now we get that x prime is ct prime is equal to x, which is ct, minus vt. Well, t is just going to be x over c, so it's minus vx over c, all times gamma. If we divide through by c, we get that t prime is equal to, ct divided by c is t, minus vx over c squared, all times gamma. And t prime, remember, is the local time. That is the time that you are measuring in your frame of reference. And t on its own is the remote time. That is to say, it is the time I measure looking at something in your world. And of course, we could have taken the other formula, which relates my value of x to your measurements. This is a formula we showed earlier. It's just the other side of the coin. And again, by substituting, we can say that x is ct equals x prime, which is ct prime, plus vt prime, which is vx prime over c, all times gamma. And if we divide through by c, we get that t is equal to t prime plus vx prime over c squared times gamma. And what that shows you is that t very definitely is not the same as t prime. T is my measurement, so it's the remote measurement. T prime is the measurement you make of your clock in your system, so it's the local measurement. Let's suppose, for example, that you switch a light on and off in your frame of reference, in your train. You switch the light on and off and you measure how long it takes between switching the light on and the time that you switch it off. That will be in your system T prime. Now, of course, in your system, the light doesn't move because the scale and the light are in the same frame of reference. So your light is fixed, which means that x prime for you is going to be 0. So this formula reduces to t is equal to t prime times gamma because x prime is 0. And as we've already shown, that that gamma is 1 over the square root of 1 minus v squared over c squared. If the square root of 1 minus v squared over c squared is between 0 and 1, which is what we showed before, then 1 over this term is going to vary between, gamma is going to vary between 1, when the denominator is 1, and infinity, when the denominator is 0. So in other words, gamma is going to be 1 or greater than 1, which means that t is going to be greater than t prime. So if you measure a certain time interval whilst that light is on, I will say, using my clock, that my time is longer. In other words, I will accuse you of having a clock that is running slow. And this is called time dilation. It says a moving clock appears to run slowly. Once again, you're not going to notice that if you're travelling in a train at 30 miles an hour, but you would notice it if the train was travelling at speeds approaching the speed of light. So let's look at some examples of length contraction and time dilation. First we'll do length contraction. Here is Alice on board a train travelling at 0.9 times the speed of light. And she is going to measure the length of a rod, and we'll say that she measures it as 3 meters. On the platform is Bob, and he is going to measure the length according to his own meter scale, and we know, because we've shown, that the Bob's measurement, the remote measurement, x, is equal to Alice's measurement, the local measurement, times the square root of 1 minus v squared over c squared. We showed that earlier. X prime is Alice's measurement, x is Bob's measurement. Alice measured 3, so x is equal to 3 into the square root of 1 minus, well, v is 0.9 times c, so we've effectively got minus 0.9 squared here, which is minus 0.81. And that is 3 into the square root of 0.19, and that is very roughly equal to 1.3 meters. So what we've said is that Alice measures the rod to be 3 meters long, but Bob will measure it to be 1.3 meters, significantly shorter. And that is because Alice is travelling at 0.9 times the speed of light. And so there's a significant length contraction. What about time dilation? Well, once again, here is Alice on the train moving at 0.9 times the speed of light. And she's going to switch a light on and off and time the time interval between the light being on and going off. And that's 2 seconds. Essentially, the light was on for 2 seconds. Here is Bob on the platform, and he is going to measure that time using his own clock. And as we showed before, the time that Bob will measure, the remote time, is equal to the time that Alice will measure, which we call t prime, plus vx prime over c squared, all to the gamma. Now, x prime is 0, because in Alice's frame of reference, the light is not moving. The scale and the light are on the train. So the light is stationary in Alice's frame of reference. So x prime is 0. And all we now get is that t is equal to t prime times gamma, which of course is t prime divided by the square root of 1 minus v squared over c squared. And now we can do the same as before. We can say that t is equal to t prime. Well, Alice, we said, measured that to be 2 seconds. So t prime is 2 divided by the same as we had before, v squared over c squared. Well, that's going to be 0.9 squared, which is 0.81. 1 minus 0.81 is the square root of 0.19, and that comes out to approximately 4.59 seconds. So what we're saying is that Alice measures the light as taking 2 seconds, but Bob measures the light to be on for 4.59 seconds. Bob says, obviously my watch is right, so 4.59 seconds is correct. If you, Alice, only measure 2 seconds, it must be because your watch is running slow. So he accuses Alice of having a watch that is running slowly. Of course, that's not true. This is just the consequence of special relativity. Now, one intriguing consequence of this is that if a moving clock runs slow, and that means that every clock runs slow, including your body clock, that if you are travelling at speed, you will age less than someone who is stationary. So you could envisage the following experiment. Here is the Earth, and here is a space traveller who travels in this kind of orbit and maybe takes 40 years. Now, if that travelling is close to the speed of light, then what we're saying is that their clock, because they're the moving part, their clock will run slow. Now, this is truly not special relativity because, of course, in order to go round in a circle like this, you have to accelerate. And once you accelerate, you get into general relativity. But I'm just trying to make a point here that if you travel at close to the speed of light for a period of 40 years, you will come back to the Earth tens of thousands of years into the future. So you age by only 40 years, but you will return to the Earth as it will be in 10,000 years' time. However, there's one big drawback. You can never go back. You can only ever go forwards in time this way. But that might be an intriguing piece of space travel for the future. Now, an experiment has actually been done to demonstrate the reality of time dilation. And it's all to do with particles called muons and muon decay. Muons tend to be created in the upper atmosphere as a consequence of interaction of rays and particles that come from the sun, and then they fall down to Earth. But as they fall to Earth, they decay. The important thing is that the half-life, that is, the time for the number of muons to halve, is 1.5 microseconds. And they travel at almost the speed of light, about 0.99 times the speed of light. So an experiment was done on top of a mountain where the number of muons were measured per minute at the top of the mountain and also at the bottom of the mountain. And what they found was that at the top of the mountain there were about 500 per minute recorded. And at the bottom of the mountain about 290 per minute were recorded. And the height of the mountain, the distance between reading 1 and 2, was about 2,000 metres. Now we can do a simple calculation to find out how long it takes to fall 2,000 metres. Well, the time is simply going to be the distance divided by the velocity. In this case, the distance is 2,000 metres and the velocity is 0.99 times the speed of light. And that comes out to approximately 6.73 microseconds. And since the half-life is 1.5 microseconds, this is more than 4 half-lives. So if there were 500 at the top, then you would expect that after one half-life, that would have fallen to 250. After a second half-life, you'd be down to 125. After a third half-life, you would be down to 62. And after a fourth half-life, you'd be down to only 31 counts per minute. But in fact, there were 290 counts per minute, which suggests that for the muon, the time has slowed. And we can now see why. We can apply the same self-formula that we did before, t prime, which is the remote time, that's the time we measure, is equal to the time that the muon measures, divided by the square root of 1 minus v squared over c squared. Well, the time we measured was 6.73 microseconds. And that's going to be equal to the time that the muon measures, divided by 1 minus essentially 0.99 squared, because the velocity of the muon is about 0.99 that of the speed of light. And this is the square root of course. And that means that t is equal to be 6.73 times the square root of 1 minus 0.99 squared. And that comes out to be 0.94 microseconds, which isn't even one half-life, because the half-life is 1.5 microseconds. So what does that say? We say it took 6.73 microseconds for the muons to fall this distance, and they should have gone through 4 half-lives, which means that if the reading at the top is 500, then by the time we've got down to the bottom, there should only be a reading of 31. The muon says, no, 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 no. It actually only took me 0.94 microseconds to fall, because that's the relativistic correction. And 0.94 microseconds isn't even one half-life, which is why we haven't even halved the reading by the time we get to the bottom. And that experiment has actually been done and is a demonstration of the effect of the relativistic effect of muons travelling at close to the speed of light, and the fact that you get time dilation. Finally, it can also be shown that mass is relativistic, and that the remote mass, if you like, is equal to the local mass, that is the m prime, divided by the self-same correction factor, square root of 1 minus v squared over c squared. So that as v approaches the speed of light, then you will see that this term becomes becomes 0, and that means that the overall term, the mass will become infinite. Let me just say that again. As v tends to c, then v squared over c squared is 1, 1 minus 1 is 0, and m prime divided by 0 is infinite. So m becomes infinite. And that is why massive objects can never get to, let alone surpass, the speed of light. Because as they get faster and faster, they get heavier and heavier. And as they approach the speed of light, their mass becomes infinite, which means you need an infinite force to accelerate them, because force is mass times acceleration. And if the mass is going to be infinite, you're going to need an infinite force to accelerate them to go a little bit faster to reach the speed of light. So any massive particle, or indeed massive anything, can never get to the speed of light. And that also means that things that do travel at the speed of light, like photons, obviously have no mass. Because if you've got no mass to start with, then you don't get an infinite mass as you travel faster. So massless particles travel at the speed of light. Anything with mass is incapable of getting to the speed of light. Now we can take this term here and we can subject it to what's called a binomial expansion. Now what binomial expansions basically say is that if you've got a term 1 plus x to the power n, that will equal 1 plus nx plus some other terms which under certain circumstances you can largely ignore because they are very small. If we take this approach and we subject it to this here, this formula reduces to m equals m prime into 1 minus v squared over c squared to the minus a half. Minus a half essentially means 1 over the square root of this term. And now if we use this here, we get that m equals m prime into, well, this term expands into 1 plus n is minus a half, x is minus v squared over c squared. So you've got minus a half times minus v squared over c squared is plus v squared over 2c squared. And that is essentially a binomial expansion of this term using this approach. There are, of course, some other terms, but they get progressively smaller, particularly if v is very much less than c. Well, that means that m is equal to m prime plus m prime v squared over 2c squared. And now let's multiply all the way through by c squared. mc squared equals m prime c squared plus m prime v squared over 2. You might recognise this, mv squared over 2, haven't we met that before? Isn't that kinetic energy? So this must be an energy term, mc squared must be an energy term. So we've got energy is equal to m prime c squared plus a half m prime v squared. That's kinetic energy. That is what is often called rest mass energy. And it's the way in which essentially Einstein developed the formula that everybody knows, E equals mc squared. So finally, let me just remind you of the formulae, the relativistic formulae that govern special relativity. In terms of distance, we have length contraction. We say that the remote measurement is equal to the local measurement times the square root of the correction factor, 1 minus v squared over c squared. As far as time is concerned, the remote time is equal to the local time divided by the correction factor, 1 minus v squared over c squared. And as far as mass is concerned, the mass that we measure is equal to the local mass, m prime, divided by 1 minus v squared over c squared. And those are the three formulae associated with special relativity.